Imagine waking up one morning and finding out that the universal speed limit, the one rule every sci-fi fan quotes like gospel, has been bending behind our backs. Not broken, just bending, the way a sleepy cat bends the rules of gravity by melting off the couch. We grow up hearing that nothing can travel faster than light, full stop, no exceptions, no backstage passes. Light is the cosmic speed champion, the Usain Bolt of the universe. Except Bolt never had his velocity written into the instruction manual of reality. Light did. And yet, the more scientists stare at this supposedly rock-solid limit, the more it behaves like one of those dramatic friends who says they are absolutely leaving the party, and then shows up in your selfie 10 minutes later. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now, let's begin. But let's slow down, ironically, because the reason we think the speed of light is fixed, precise, and carved in cosmic stone is that we have been told the same story for generations. Light travels at roughly 186,000 miles every second. That number gets repeated so often, it starts to sound like something nature declared solemnly at the beginning of time. But what if nature is not the one enforcing this rule? What if we humans, in all our scientific enthusiasm, accidentally built part of the rule book ourselves? And what if light, being the universe's favorite rebel particle, has been playing along while quietly doing weird things when we are not paying close enough attention? Start with the name itself, the speed of light. It sounds like the kind of phrase someone would whisper while unveiling a sacred relic. But really, it is just a description we invented because humans like labeling things, especially when those things flash dramatically from place to place. And sure, the speed of light is fast. So fast you could shine a flashlight at the moon, and the beam would get there before you managed to finish saying the word flashlight. But the number we use to define this speed is not so much a discovery as it is a cosmic handshake agreement. And if that sounds suspiciously philosophical, do not worry. We are not drifting into the land of incense and guitar music. We are drifting into the land of science, which is somehow even stranger. Here is the real twist. For something treated as a strict limit, light has a habit of acting like it is auditioning for a magic show. In some places, it cruises along at its usual speed. In others, it slows down dramatically, almost like it encountered cosmic molasses or decided to take a scenic detour. And in a few special cases, it even appears to move faster than usual, because apparently the universe likes loopholes as much as lawyers do. You hear all this and start to wonder whether the speed of light is a law or a suggestion, a cosmic guideline, a polite request from the universe that light usually respects but occasionally ignores, just to keep scientists humble. What makes this so thrilling is not just that light behaves unpredictably, but that it has been doing so the entire time we have been watching it. Yet the story told in classrooms is simple. Light is fast, light is constant, the end. It is neat, it is tidy, and it does not give anyone a headache. But science is not here to be tidy. Science is here to present us with cosmic puzzles wrapped in enigmas, sprinkled with wait what moments. And the speed of light offers those moments by the bucketful. Because once you start poking at the idea of a universal speed limit, everything gets delightfully complicated. If light can be slowed, what does that mean for the rule itself? If it can appear to go faster, what does that mean for causality and information? And if the value of its speed is defined by us rather than discovered in nature, what does that mean for our measurements, clocks, and understanding of space itself? The questions pile up faster than light can answer them, which is ironic given the topic. And yet the mystery is exactly what makes it fun. The universe could have chosen to be boring and straightforward. It could have made light behave like a disciplined, respectable beam that never strayed from its cosmic lane. But instead, the universe gave us something far better, a speed that seems fixed until it is not, a rule that looks strict until you read the fine print, and a cosmic constant that occasionally winks at the audience. Light is like that friend who insists they are predictable and then unexpectedly orders a pet lizard online at 3 a.m. So as we dive deeper into this adventure, keep your curiosity switched on. The speed of light is not the simple, clean number you were taught. It is stranger, more flexible, more dramatic, and far more mischievous than anyone expected. If you think you already know what it is, that is exactly why you are here. The story you grew up with is only chapter 0. The real tale begins now. Speed is one of those things humans think we understand because we spend our whole lives measuring it. We compare cars, sprint times, internet connections, microwave countdowns, anything that moves, we rank. We celebrate fast things like race cars and cheetahs, and complain about slow things like elevators, sloths, and every file that says 1 minute remaining, but secretly means brace yourself for disappointment. In our daily world, speed is simple. The faster something gets from one point to another, the better. That is the entire philosophy behind roller coasters, pizza delivery, and the way people sprint through airports when boarding is final call. But our everyday idea of speed is hilariously bad at preparing us for the cosmic version. Out here on Earth, being fast just means being faster than something else nearby. A cheetah is fast because it can outrun a gazelle. A jet is fast because it can outrun a storm. But imagine trying to explain speed to a galaxy. Galaxies drift for billions of years like giant, graceful ice skaters who have zero urgency. They are not impressed by anything that burns fossil fuel. To a galaxy, even our fastest rocket looks like it is stuck in cosmic mud. So our sense of speed is shaped by a tiny bubble of human-scale experience, where distances are friendly, time scales are short, and nothing is so far away that you have to factor in the age of the universe to reach it. Now drop light into this picture, light, which moves so quickly it makes everything else look like it is practicing for a very slow parade. It zips around at a pace that sounds less like a speed and more like a dare, roughly 186,000 miles every second. If you tried to imagine that speed using normal human comparisons, your brain would stage a protest. Light could circle Earth 7 times between 2 blinks. It could go from the sun to Earth in about the time it takes you to say, "Wow, that is," and then it is already here. It is unstoppable, relentless, dramatic. the diva of the universe. But here is the cosmic punchline. Even though light is incredibly fast, in the grand scheme of the universe, it is also unbelievably slow. Not slow in a mocking, did it forget its keys way, but slow in the sense that the universe itself is outrageously, absurdly large. The kind of large that makes your brain quietly back away and pretend it saw nothing. Light has a head start of 186,000 miles per second, and the universe still shrugs and says, "Cute. Try again." This is where the cosmic world starts messing with our intuition, because in daily life, speed gets you places quickly. Your bike gets you down the street. A car gets you downtown. A plane gets you across continents. But light needs years, literal years, to get anywhere interesting. If you reach up right now and point at the nearest star beyond the sun, the light hitting your fingertip started its journey when your phone was probably still 2 models old. If you look at Andromeda, the nearest big galaxy, the light reaching your eyes tonight began traveling long before humans invented agriculture. It crossed unimaginable gulfs, while our ancestors were busy discovering that fire was not just pretty, but also useful. So even though light seems fast by human standards, the universe has a habit of laughing at those standards. Imagine running a marathon where the finish line is moved farther away every time you get close. That is what light deals with. And not just a little bit farther. Cosmic distances stretch so dramatically that light might as well be muttering, "This was not in the job description." Our brains simply are not built to juggle these scales. We evolved to think about distances measured in footsteps, not light years. A light year is how far light travels in 1 year. And even that is such a colossal distance that you could stack every road on Earth end to end and still not scratch the surface of it. Light year is not a friendly unit. It is the universe politely telling us we need bigger rulers. What makes things even stranger is that light is both the fastest thing in existence and still not fast enough to make the universe feel small. If anything, light exposes how ridiculously oversized everything is. It is like turning on a lamp in a gigantic cavernous room, and the light only reaches a few steps before darkness takes over again. The lamp is bright, but the room is enormous, and suddenly the lamp feels tiny, even though it did not change at all. So when people say the speed of light is the ultimate limit, it is true in a practical sense, but it also hides a deeper truth. That limit is only meaningful to us because we live slow, tiny lives on a small, friendly planet. If we lived on a galactic scale, we would probably think the speed of light is adorably sluggish, like watching a snail try to commute to another city. Light is the universe's speed champion, yes, but even champions get humbled when the racetrack is the size of everything that exists. And that is the heart of the mystery. Light is fast enough to feel magical, yet slow enough to remind us how enormous and ancient this universe is. It bridges the gap between everyday intuition and cosmic reality, showing us that speed is not just about motion, it is about perspective. The faster something moves, the more the universe seems to stretch around it. And the more the universe stretches, the more light reveals just how small we truly are. If you grew up thinking the speed of light was a scientific treasure dug out of the universe like a glowing cosmic gemstone, you are not alone. Most of us imagine scientists measuring it by pointing lasers at things, crunching numbers, and eventually announcing, "We found it, the sacred speed." But the truth is far stranger and much more human. The speed of light is not a number we discovered. It is a number we decided. We chose it. We literally fixed its value by definition. The same way a restaurant might declare that every slice of pie is officially 1/6 of a pie, no matter how uneven the cuts look. To understand why that happened, you have to go back to a time when scientists were desperately trying to measure the speed of light the old-fashioned way, with clever experiments, awkward setups, and sometimes questionable life choices. Early researchers tried using rotating mirrors, blinking lanterns, astronomical observations, and even speed-of-light relay races between distant mountaintops. The results were impressive for their era, but they had the consistency of a toddler's handwriting. Every measurement gave a slightly different answer, and the precision improved only because scientists refused to accept that the universe might enjoy messing with them. But the real drama started when science developed clocks, really good clocks. Clocks so precise they could measure time beautifully, but required a perfect stable way to measure distance. And that is when scientists hit a weird problem. Measuring distance and measuring time are not separate tasks anymore. They are tangled together like headphones in a pocket. If you want to know how far something is, you measure how long it takes light to get there. But to measure how fast light moves, you need to know the distance in advance. It is a cosmic chicken and egg situation. So instead of letting that infinite loop torment them forever, scientists asked a bold question. What if light's speed is constant, not because we measured it perfectly, but because we choose to call it constant? What if we treat it as a built-in property of the universe, like a structural beam holding physics together? And once they asked that question, they went all in. In the late 20th century, scientists rewrote the rulebook. The speed of light was assigned a fixed, exact value by international agreement. No wiggle room, no rounding errors, no plus or minus a little bit. In that moment, light became the ultimate cosmic yardstick. Instead of using light to measure distance, they used distance to define light. The speed of light was given an exact number, and suddenly meters themselves were redefined. A meter stopped being a scratch on a metal bar in Paris and became the distance light travels in a specific fraction of a second. The universe did not hand us that number. We handed it to the universe and said, "We are using this from now on." Light became our reference, our anchor, our cosmic tape measure. This decision changed everything. It made physics cleaner and measurements more stable. It tied our definition of length to something we believed would never change. After all, light has been pretty reliable for billions of years. It moves through space with the same stubborn commitment a cat shows when blocking your laptop keyboard. But even more than that, defining the speed of light locked it into a role far beyond illumination. Light now sits at the heart of every precise measurement humans make, from satellite navigation to atomic clocks to the structure of modern communication. It is easy to think this choice sounds arbitrary, like declaring every minute to be 70 seconds just because it feels tidy. But this was not whimsical. It was a recognition that the universe ties space and time together through light. The speed of light is the link between the two, the conversion rate between meters and seconds. By fixing its value, scientists anchored the entire measuring system to one of the most stable phenomena in nature. It is like choosing the most reliable friend in your life to be your emergency contact. You pick the one who always answers the phone. And yes, it is strange to realize the universe did not mail us this number on official stationery. But science often works like this, not by waiting for nature to hand over answers, but by choosing the best framework to understand it. Scientists recognized that the speed of light is woven into the very fabric of space-time. It is not just the velocity of a wave. It is the boundary built into the geometry of the cosmos. And geometry, unlike light bulbs or rotating mirrors, does not drift over time. So the next time someone quotes the speed of light as if it were a sacred fact of nature, you can smile quietly, knowing it is partly a story of human ingenuity. The number is exact because we made it exact. The universe allows light to behave a certain way, but the digits we recite, those come from us. Light moves, nature obeys, but we write the rule book. And that rule book is not just a list of measurements. It is a promise between humans and the cosmos. If we define light speed precisely, the universe will do the rest. It will stretch space, bend time, guide photons, and keep that cosmic speed woven into every inch of reality. We did not discover the number, we decided it. And by doing so, we built a measuring system stable enough to explore the universe itself. If you picture light traveling through the universe, you might imagine it as a fearless cosmic sprinter, zipping through the void without ever stopping for breath. And in the emptiness of space, that is almost true. Light practically flies with its shoelaces on fire. But bring it into a world full of stuff, and suddenly the mood shifts. Light goes from sprinting champion to a commuter trapped behind a tractor on a 2-lane road. It is not that light becomes tired or confused. It is the environment slowing it down, the same way a bustling crowd slows even the fastest runner. Light inside a material is basically the universe reenacting rush hour. The reason light slows down is surprisingly down to earth. Materials are made of atoms, and those atoms are not just sitting around politely. They are buzzing, vibrating, and flaunting their electric fields like tiny social butterflies. Every time light enters a material, say water, glass, or the transparent slab you probably smudged with fingerprints, its clean, uninterrupted journey turns into a chaotic game of atomic pinball. The photons that make up light are not truly strolling slowly through the material. Instead, they are constantly being stopped, absorbed, re-emitted, jostled, delayed, and sometimes heckled by the atoms in their way. This stop-and-go behavior is why light moves at different speeds in different materials. In air, which is mostly empty space pretending to be something, light slows down just a tad. In water, the slowdown becomes more dramatic. It is like switching from a bicycle lane to a sidewalk covered in people handing out flyers. And glass? Glass is where light sighs deeply and accepts that its day just got more complicated. It moves through glass at only about 2/3 of its speed in a vacuum. To light, glass is a cosmic school zone with a very strict speed limit. This might sound strange because glass looks clear. If something is transparent, you would think light slides through it like a champion figure skater. But transparency and speed are completely different things. Being transparent means the material lets light through without eating it like a photon snack. But it does not mean light gets VIP access. Light still has to weave through a dense forest of atoms, and that weaving slows it down. Clear does not mean fast. It means not entirely rude. Different materials slow light by different amounts because each material's atoms interact with light in their own signature way. Some atoms are like overly enthusiastic fans, grabbing at every photon that passes. Others barely react unless the photon hits the exact energy level they care about. This difference is what scientists call the index of refraction, which is just a fancy way of saying how much a material makes light tap the brakes. Water gives light a gentle nudge. Diamond, on the other hand, practically tackles it like a linebacker. Light in diamond moves so slowly compared to its speed in empty space that you could almost imagine it rolling its eyes the entire way. What makes this even more amusing is how dramatically these differences change the behavior of light. Snell's law, the reason your straw looks broken in a glass of water, is just light trying to navigate these speed changes. When light goes from air to water, it slows down, but unlike a polite driver, it does not signal. It bends, like it is trying to sneak past the border unnoticed. Every time it crosses between materials with different speeds, its direction shifts. It is the cosmic equivalent of stepping onto a moving walkway and suddenly veering sideways. If that sounds dramatic, consider what happens in fiber optic cables. These cables, which help funnel your videos, calls, and random cat memes across the world, trap light inside by forcing it to bounce around like a hyperactive glowworm. The trick is that the inside of the fiber is made of a material where light moves slower, and the outside is made of something where light would move slightly faster. That difference in speed creates a boundary that keeps light trapped inside, bouncing from wall to wall like it is trying to escape, but remembering it promised to deliver your streaming show first. But the champion example of light slowdown happens in substances called Bose-Einstein condensates. In these exotic materials, cooled to temperatures so low they would make Antarctica feel tropical, scientists have slowed light to the speed of a leisurely human walk. Imagine telling light, the cosmic sprinter, that today it is required to stroll. That is the level of bizarre these materials reach. Light crawls so slowly that you could practically pace beside it and say, "How was your day?" This is not because photons suddenly became lazy. The material manipulates them in such a wildly coordinated way that their progress becomes glacial. This might make light sound fragile, but slowing down does not hurt it. Light is not losing energy or dragging its feet. It is simply interacting with the environment. Once it exits the material and returns to empty space, it instantly accelerates back to its usual speed, as if nothing happened. Imagine running full speed through a crowd, getting slowed down by hundreds of high fives, and then instantly regaining top speed once you burst through the other side. And this cosmic traffic jam is not just a curiosity. It is the basis for lenses, cameras, microscopes, telescopes, fiber optics, and nearly all optical technology. Every device that bends, focuses, or guides light relies on the fact that materials slow it down. If light behaved the same everywhere, your glasses would not focus anything, telescopes would not magnify stars, and microscopes would be about as useful as staring intensely at dust. So the next time you look through a window, stare at a glass of water, or hold a diamond necklace up to the light, remember this: light is moving through those materials like a traveler trapped in a particularly enthusiastic crowd. It's still the fastest thing in the universe, but inside matter, the universe likes to remind it to watch its step. If you remove absolutely everything from a place, no air, no dust, no atoms, no rogue molecules sneaking in through the cosmic back door, you are left with a vacuum. And you might imagine a vacuum as simply empty, a lonely corner of the universe where nothing happens because nothing is there to do the happening. But the universe, being the overachiever it is, turns that emptiness into the fastest racetrack in existence. When light moves through a vacuum, it reaches its ultimate, unrestricted speed, as though the universe rolled out a flawless cosmic highway with no speed bumps, no speed limits, and no police cruisers hidden behind nebula-shaped billboards. The reason vacuum speed is so special starts with the fact that a vacuum is not just empty, it is profoundly empty. Every material you can imagine, whether it is water, glass, diamond, fog, jello, or the air you are breathing, is full of particles that love to interrupt light, like an enthusiastic audience member shouting commentary at a movie. But a vacuum gives light nothing to interact with. No particles grab it, no atoms delay it, no molecules distract it. Light zips through the vacuum with the smooth, uninterrupted confidence of someone walking into a room and realizing all the chairs automatically swivel to face them. But this does not mean the vacuum is a boring blank. Far from it. The vacuum is like a stage after the actors have gone home, but the lights are still humming, with possibilities, fluctuations, and invisible fields woven into its structure. When scientists talk about the vacuum, they do not mean absolute nothingness. They mean the lowest possible energy state that still contains the quantum equivalent of background static. Tiny blips of energy appear and vanish constantly. Particles flicker in and out of existence like cosmic fireflies powered by uncertainty. If the universe had an engine idle sound, this would be it. Yet, in spite of all that quantum bustle, nothing in the vacuum gets in light's way. Light does not slow down because these fluctuations do not grab it the way atoms do. Think of the vacuum as a crowd full of extremely polite ghosts. They are technically present, but they are so shy and so insubstantial that light glides right through without even noticing they were there. It is the only environment where light is free from the cosmic equivalent of traffic, detours, and people walking slowly in the grocery store aisle. This freedom is why scientists treat the speed of light in a vacuum as the fundamental baseline speed of the universe. It is the one speed that does not change. Everything else, light in water, light in glass, light inside your eyeball, is just the universe adding scenic delays. But the vacuum, that is the pure, unfiltered, cosmically sanctioned pace. It is the speed that sits at the heart of how space and time work. It is the speed that links 1 second to 1 meter. It is the speed that determines how quickly information and causality move. The vacuum speed is so foundational that if it ever changed, physics would probably collapse into a puddle of confused equations. The beauty of vacuum speed is that it feels like the universe giving light its best shot. Picture a race where every contestant is already fast but must dodge obstacles. Then imagine clearing the entire track until only light remains, and suddenly it breaks into a stride so perfect that even time seems impressed. This is what happens in the vacuum. Light reveals its full capability, and the universe uses that capability to shape the rules. This is also why the universe seems to treat the vacuum as both canvas and blueprint. Light traveling through vacuum does not merely move, it sets the upper boundary for motion itself. Nothing with mass can reach that speed, because mass requires energy to move, and approaching vacuum light speed demands infinite energy. Infinite energy is the universe's polite way of saying, absolutely not. Light has no mass, so it gets to enjoy the one perk that mass cannot, gliding at full cosmic acceleration without tearing itself apart. The vacuum is also the great equalizer. No matter where you are in the universe, on a drifting asteroid, inside the orbit of a distant star, or floating through a patch of intergalactic emptiness, the vacuum speed of light is the same. The laws of physics treat it as the universe's signature move. Every patch of vacuum, no matter how lonely or remote, offers light the same perfect racetrack conditions. It does not matter if you are near a star cluster or in a region so empty you could count the particles on one hand. The vacuum provides the same pristine conditions for light to sprint at top speed. Yet there is something almost poetic about this. Light moves fastest not where the universe is most alive and crowded, but where it is most silent. The emptier the space, the purer the motion. Vacuum speed is a kind of cosmic minimalism. Remove everything unnecessary, strip the environment down to its quantum bones, and suddenly light reveals its maximum grace. If atoms are the universe's version of clutter, the vacuum is its perfectly organized desk drawer where everything runs exactly as intended. And despite its name, the vacuum is not a void of insignificance. It is a stage for the universe's most fundamental performance. When light races through it, unimpeded and unstoppable, it tells us how space stretches, how time bends, and how information flows. The vacuum is not nothing. It is the backdrop against which everything becomes possible. So while materials slow light down and twist its path, the vacuum gives light room to be itself, No obstacles, no delays, no cosmic traffic jams, just pure, unrestrained motion. In the grand scale of things, the vacuum is not the absence of reality. It is the arena where reality reveals its deepest rules. If you could zoom in far enough to watch light in slow motion, really slow motion, the kind where time crawls like a snail reading a novel, you would see something surprising. Light is not a stream of tiny glowing pellets racing through space like cosmic confetti. It is a dance, a self-sustaining, self-propelling, endlessly intertwining dance between electric and magnetic fields. Light is what happens when these two invisible forces decide to hold hands and sprint together across the universe. To understand why this is so extraordinary, imagine two partners who move so well together that neither one ever steps on the other's toes. The electric field swings forward, and the magnetic field responds instantly, forming a rhythm that repeats itself over and over as they travel. The movement of one creates the other, and together they form a wave that can fly through the emptiest vacuum or the densest astrophysical playground. Light exists not because something pushes it forward, but because these two fields generate one another in an endless loop, like the world's most coordinated relay race. Electric fields and magnetic fields are not strangers to us, even if they are invisible. They shape everything from how your phone charges to why magnets stick to your refrigerator door. But when they combine in exactly the right configuration, perpendicular to each other, and perpendicular to the direction of travel, they become something far more dramatic. They become light. Not just the light you can see, but every form of electromagnetic radiation, radio waves, microwaves, ultraviolet rays, X-rays, all the way up to gamma rays. Every one of them is built out of this same interwoven duet of fields. Now here's the twist. Those fields do not just create light's existence, they dictate its speed. The speed of light is not an arbitrary pace chosen by nature because it liked the number. It is a direct consequence of how electric and magnetic fields respond to each other. The universe has built-in properties, constants that describe how strong electric fields are and how strong magnetic fields are. When you combine those two cosmic traits, something magical pops out. A speed, not just any speed, but the speed. The fastest speed. The speed light must travel because of the way the fields interact. If that sounds like the universe hiding a cheat code in physics, you are not wrong. Imagine if every time you clapped your hands, your friend instantly did jazz hands. Then their jazz hands caused you to clap again. Each reaction is tied to the next. The rate at which this happens sets the pace of your bizarre dance. That pace, scaled up to cosmic proportions, is the speed of light. It is built into the equations that govern electricity and magnetism, equations describing the stiffness of space itself. Light is not speeding through a racetrack. It is riding the pulse of the universe's own field dynamics. This also means that light does not need anything to travel through. It does not require a medium or a substance to wiggle. The fields that create it are part of space already. They exist everywhere, even in perfect vacuum. Light is simply those fields shaking hands with each other so rapidly and so perfectly that the motion becomes a wave racing through space. This is why light moves effortlessly through the vacuum, while sound needs air, water, or walls to travel. Sound needs particles to vibrate. Light only needs the structure of space itself. But the story becomes even more fascinating when you realize that these fields anchor light's speed so tightly that nothing, not even the universe expanding, can make it change. If space were a giant trampoline and you threw a ball across it, the ball would slow as the fabric stretched, but light does not. Light's speed is not determined by the fabric of space. It is determined by how that fabric allows electric and magnetic fields to influence each other. Even if the universe wrote under construction signs everywhere, light would still travel at the same pace, shrugging off cosmic chaos with the confidence of someone who always arrives exactly on time. There is something quietly elegant about this. The speed of light is not set by particles or materials or even energy. It is set by the relationship between two invisible forces that exist everywhere and always have. These forces do not care whether the universe is hot or cold, dense or empty, expanding or stable. They braid together in the same way no matter what, and their partnership produces the same result, a wave that moves at the fastest speed the universe allows. Electric and magnetic fields are also why light carries information. They can wiggle in complicated patterns, patterns that encode music, voices, images, data, even instructions beamed to spacecraft millions of miles away. When you listen to the radio, you are listening to ripples in these fields. When you read on your phone, the screen splashes patterns of electromagnetic waves into your eyes. When you heat leftovers in the microwave, that is just a higher energy version of the same phenomenon. Every modern device that speaks wirelessly is really whispering in the language of oscillating fields. Yet despite how essential light is to everything around us, the fields that create it remain invisible. They do not glow, shimmer, or hum ominously. They simply exist, waiting to interact. You only know they are there because when they dance together, they create illumination, color, warmth, and information. Without their silent choreography, the universe would be a dark, cold expanse where nothing could communicate with anything else. There is something almost poetic in that. Light, the thing that reveals the world to us, is itself made of things we cannot see. And its speed, the number we treat as a cosmic law, is nothing more than the natural tempo of two fields weaving in perfect harmony. The next time you flip on a lamp or watch the sunrise, remember, you are not just seeing brightness. You are watching electric and magnetic fields waltz at the exact pace the universe allows, slipping through space with a grace that shapes reality itself. If someone told you that scientists once slowed light down to the speed of a casual stroll, you might assume they were joking, or that the scientists in question were suffering from severe sleep deprivation. After all, light is famous for being the universe's fastest traveler. It blasts across space with the confidence of someone who always gets the last slice of pizza. But in laboratories around the world, Researchers have coaxed this cosmic sprinter into moving so slowly that a toddler could outrun it. And in certain jaw-dropping cases, they have made it stop altogether. Not pause, not hesitate. Stop, like a photon at a red light that lasts several seconds. These strange experiments didn't start as attempts to humiliate light's reputation. They began as a quest to understand how information and energy move through matter under extreme conditions. One of the most famous cases involved a team who cooled a cloud of atoms to temperatures so low that even the atoms themselves seemed confused about why they were still awake. This wasn't your everyday cold. This was colder than outer space, colder than logic, colder than your cat's opinion of you after a bath cold. At these temperatures, the atoms merged into a bizarre state of matter where they all behaved like a single giant, perfectly synchronized quantum entity. Into this strange atomic cloud, the researchers sent a beam of light. Under normal circumstances, light would zip right through such a small volume faster than you can say, "This is ridiculous." But once inside, light found itself surrounded by atoms that were so coordinated, so slow-moving, and so collectively weird that they changed the rules entirely. As the beam entered the cloud, its energy didn't simply pass through. Instead, the atoms grabbed hold of the light's information, its pattern, its identity, and started passing that information along from atom to atom like they were participating in a cosmic game of telephone. The result was stunning. The beam slowed to a pace that would make even the slowest walker feel athletic. Imagine a photon drifting through the room at a speed where you could step beside it and offer it a motivational pep talk. That is the level of slowdown these experiments achieved. And, as if that wasn't wild enough, the researchers then found they could stop the light completely, not destroy it, not absorb it, just stop it, freezing its information in place for a moment before releasing it again. It was as though the light had been politely asked to wait, and for the first time in cosmic history, it listened. This feat wasn't about breaking the laws of physics. It was about exploiting possibilities the laws already allow. When light passes through everyday materials, it interacts with atoms and slows down, but it never stops outright. The idea that one could halt light required conditions so extreme and unusual that even the atoms needed to be talked into cooperation. But once those conditions were created, the behavior of light changed dramatically. It was still light, still carrying the same fundamental properties, but its movement, the characteristic zipping motion we take for granted, became negotiable. One of the key reasons this works is that light can store its essence, the information that makes it light, inside matter. When the atoms passed along the pattern of the beam, they weren't acting like thieves. They were acting like couriers. The light's identity became imprinted on the system. And when the researchers wanted the beam back, they adjusted the conditions and let the atoms release that stored information back into space, where it reassembled into the same beam that it entered. You could think of it like checking a coat at an extremely advanced quantum coat check counter, except the coat is a traveling wave of electromagnetic fields, and the coat check employees are atoms barely above absolute zero. Another set of experiments took this even further by slowing down individual pulses of light to speeds you could measure without a stopwatch. Instead of racing at its usual pace, the pulse crept along like someone tiptoeing through a room full of sleeping grandmothers. These setups didn't require the absurdly cold temperatures of the earlier experiments. They used exotic materials designed to interact with photons in precisely the right way. By carefully tuning these materials, researchers essentially set up a series of roadblocks that forced the light to move forward only when conditions allowed. It didn't destroy the beam, it just stretched its progress into a series of tiny, painfully slow steps. What these experiments reveal is not that light's cosmic speed limit is broken, but that the limit applies only to free light, light that's not interacting with matter. Once light enters a material engineered for extreme manipulation, the game changes. The photons become reluctant travelers, their journey dictated by the complex handshake between energy and matter. The universe isn't violating its own rules. It's showing how flexible those rules can be when conditions are tuned with exquisite precision. These discoveries aren't just scientific party tricks. They have opened pathways for futuristic technologies involving stored light, quantum communication, and information processing that might someday make our current devices look as outdated as stone tablets. If you can stop light, you can store information at speeds we can barely imagine. And if you can slow light to a walking pace, you can create devices that control photons with the precision of a sculptor shaping clay. Light may be the universe's fastest traveler, but in the hands of determined scientists, it turns out to be surprisingly negotiable. Under the right conditions, even the cosmic sprinter can be convinced to pause, take a breath, and wait patiently, if only for a moment. If slowing light to a walking pace sounds like a magic trick, the opposite scenario feels like full-blown wizardry. Situations where light appears to move faster than its usual cosmic speed limit, faster than the fastest thing in existence, faster than the number we treat as sacred. It sounds like the universe violating its own rules, or at the very least bending them so dramatically that the rulebook crumples. But here is the strange truth. Under the right conditions, light can appear to travel faster than its usual pace, and yet nothing illegal happens. The speed limit remains intact. Physics does not have to call its lawyer. The trick lies in understanding a subtle distinction between the speed at which light itself travels and the speed at which light's influence or shape appears to move. Think of light not just as a thing that zips through space, but as a wave, something that has a crest, a shape, a pattern. In certain environments, those patterns can shift, stretch, or rearrange in ways that make it seem like the wave is moving faster than the true underlying motion of energy. The fast part is the illusion, like watching a shadow sweep across the ground at high speed, even though the actual object casting it is moving slowly. One of the most dramatic examples of this happens when light passes through exotic materials crafted to manipulate waves in ways nature never does on its own. These materials, often built with microscopic structures that coax light into strange behavior, can make a pulse of light emerge earlier than expected, as though it jumped ahead of schedule. It is not that the photons sprinted faster than the universal speed limit. Instead, the shape of the pulse was altered. The front of the wave became weaker while the middle shifted forward, giving the appearance of a leap. The pulse looks like it outran itself, but the truth is far more nuanced. The material reshapes it the way a sound engineer shifts a musical track without speeding up the singer. This might sound like linguistic gymnastics, but the universe is very serious about this distinction. The cosmic speed limit applies to information and energy, things that can change outcomes. But wave shapes? Those are allowed loopholes. They can stretch, distort, or appear early because the universe does not worry about them causing paradoxes. It is like allowing shadows to run wild because no one is worried about shadows breaking causality. Things get even stranger when we look backward in time, toward the early universe. Moments after the Big Bang, the cosmos was a roiling sea of plasma, so dense and so energetic, you could not have found an atom with a map and a flashlight. In that environment, light behaved in a way radically different from the clean, elegant beams we picture today. It wove through a soup of charged particles that scattered and deflected it endlessly. But despite this chaos, the collective behavior of these waves, their group motion, could move at speeds that seemed to outperform light's usual pace. To be clear, no individual photon in that early universe plasma ever broke the limit. They were bouncing around like overly caffeinated pinballs, barely traveling before they were shoved in a new direction. But if you looked at the wave as a whole, the way its peaks traveled through that boiling medium, its pattern could move faster than the speed of light in a vacuum. The key is that the pattern is not carrying new information forward. It is more like watching a stadium wave sweep through a crowd. The motion seems fast, but no single person is sprinting. The crowd stays put. The illusion is in the coordination. There are modern echoes of this behavior in plasmas created on Earth. In these fiery, electrically charged environments, physicists can observe wave phenomena where the group velocity, the speed at which the wave pattern moves, exceeds the usual limit. This still does not send information faster than allowed. It is a quirk of how collective oscillations behave when electric charges and electromagnetic fields interact at extreme energies. Even though it looks like the wave is breaking the rules, it remains safely within the boundaries nature enforces. It is a loophole, yes, but a legal one. Another scenario where light appears to pull off a cosmic shortcut involves what are sometimes called anomalous dispersion conditions. Imagine a material designed so carefully that the frequencies of light passing through it are nudged in ways that make the peaks of a pulse move forward. Just as a DJ can take a sound clip and time stretch it so the beat lines up differently, some materials can shift the internal timing of light's components. The result is an output that emerges sooner than expected, almost like fast-forwarding through reality. But again, this is not information outrunning nature. It is the light pulse's shape being nudged and rearranged on its way out. Perhaps the most mind-bending example of apparent In these setups, light interacts with barriers that classical physics says it should not pass. But quantum mechanics, never one to decline a plot twist, allows light to tunnel through, emerging on the other side sooner than a naive calculation might predict. It is tempting to say it traveled faster than it should have. But what really happened is more subtle. The part of the wave most likely to appear on the other side survived and reshaped the overall pulse. No photon broke the speed limit. The wave simply rearranged itself in a way our intuition finds mischievously confusing. All these examples share one message. The universe has more imagination than we give it credit for. Light does not need to break its own rules to surprise us. It only needs the right environment. Plasma hot enough to hum with ancient entropy, materials engineered with atom-scale precision, barriers thin enough for quantum weirdness, or conditions where wave shapes take on a life of their own. The cosmic speed limit remains unbroken, but the universe leaves just enough wiggle room for light to pull off illusions worthy of a master magician. And every time scientists catch it doing so, they are reminded that even the fastest traveler in existence still has a few tricks up its shimmering sleeve. If you picture the universe as a gigantic stage, then space-time is the floorboards underneath everything, an enormous flexible surface that holds stars, galaxies, you, your neighbor's dog, and every stray particle drifting between galaxies. It looks still from our perspective, but in reality, space-time is constantly being tugged, stretched, dented, and wobbled by anything with mass. It is like a fabric that never quite settles, a cosmic carpet that ripples every time a passing object decides to throw its weight around. And right on this surface, moving across it with the conviction of someone who refuses to check a map, is light. Light, for all its speed and elegance, is deeply obedient to space-time. It does not question the terrain. It does not argue. It follows the curves and contours exactly, as though the universe hired it to be a tour guide and then gave it the world's most chaotic roadmap. This obedience is what makes the behavior of light so fascinating when gravity enters the scene. Because gravity is not a force pulling on light like a leash. It is a distortion of space-time itself. Wherever there is mass, space-time folds inward like someone sitting down on a couch cushion. Light passing nearby simply follows the new shape of the cushion. To understand this, imagine rolling a marble across a trampoline. If the surface is perfectly flat, the marble glides smoothly in a straight line. But place a bowling ball in the center, and suddenly the marble curves inward. The path bends, not because the bowling ball reached out and yanked it, but because the surface changed shape beneath it. Replace the trampoline with space-time, the marble with a photon, and the bowling ball with a star, and you've got gravity's effect on light in a single picture, minus the risk of stepping on a stray Lego. This bending of light is more than a neat trick. It changes how we see the universe. A massive object between us and a distant source can distort the light so dramatically that it creates multiple images, stretched arcs, or rings. Astronomers call this gravitational lensing, but in more dramatic terms, space-time becomes a funhouse mirror stretched across billions of light years. Light from a faraway galaxy tries to travel in a straight line, but space-time says, no, you'll want the scenic route, and sends it looping around massive structures like galaxy clusters. The resulting images are magnificent, elongated smears of ancient starlight warped into shapes that look like cosmic brushstrokes. Even more impressive is how these space-time distortions affect time itself. Light passing near a massive object does not just bend, it slows down relative to an outside observer. Not slows in the sense of trudging through matter like it does in glass or water, but slows in the sense that space-time itself is stretched. Time runs differently near massive objects, and light must navigate these stretched-out moments as though someone secretly extended the road beneath its feet. For light, passing a massive galaxy is like walking through a corridor where the floor keeps lengthening with every step. This delay is one of the reasons astronomers can see the same cosmic event at multiple different ages. A single supernova, for example, can appear in separate places in the sky because the light took different routes through warped space-time, some paths quick and direct, others long and winding. It is like receiving postcards from the same friend, but mailed from parallel roads, each with its own peculiar travel time. The event itself happened once, but space-time's creative detours turn it into a multi-episode series. These distortions become even more dramatic near extreme objects. Consider black holes, the heavyweight champions of gravity, capable of twisting space-time into spirals. Near a black hole, space-time curves so sharply that light can circle around it, caught in a gravitational cul-de-sac. In certain regions, the bending becomes so intense that light cannot escape at all. The edge of this region, the event horizon, is not a wall but a one-way curtain. Light tries to move forward, but space-time is curved inward so steeply that forward always points back in. It is the ultimate directional prank. Even around less terrifying objects like stars or planets, space-time pulls similar stunts on a gentler scale. Light passing close to the sun, for example, bends slightly, a fact first confirmed during a solar eclipse. Observers saw that the apparent position of stars near the sun shifted because their light passed through the curved space-time held by the sun's mass. It was as if the sun leaned over and whispered, "Let's make the universe look different for a moment." And the universe complied. One of the most poetic consequences of this cosmic detouring is how gravity can magnify light from distant sources. In the early universe, when galaxies were forming in chaotic clusters, their combined mass created enormous space-time dents. Light traveling through those valleys became focused, brightened, and stretched. Today, astronomers use these natural telescopes carved by gravity to study objects so distant and faint that no human-made instrument could possibly observe them. Gravity, unintentionally but generously, becomes the universe's oldest optical device. All of this paints gravity not as a strict dictator, but as a mischievous guide. It cannot change light's intrinsic speed, but it can warp the ground beneath it so effectively that the journey becomes anything but straight. Light does not fight these distortions. It glides along them, revealing the shape of space-time, the way a river reveals the shape of its riverbed. And so, when you look at starlight, you are not just seeing the glow of distant suns. You are seeing the signature of the universe's invisible architecture, the curves, dents, valleys, and folds of space-time itself. Gravity does not merely influence light, it turns every photon into a tracer of cosmic geography, mapping the universe's subtle terrain in every bend, every delay, and every detour. If you wanted to measure the universe, you could try stretching a tape measure from here to the nearest galaxy, but that would require a spool so large it would probably collapse into a black hole before you even put down the first marker. Instead, astronomers rely on the most reliable traveler they know: light. Light does not call in sick. It does not take detours on a whim unless gravity mischievously insists, and it never forgets to log its miles. Every beam that reaches us carries a timestamp, the length of time it's spent on the road. If you know how fast it travels and how long it's been traveling, you can estimate the distance it has crossed. Light's travel time becomes a ruler, not carved from wood or metal, but from the steady ticking of cosmic seconds. When you look at your reflection in the mirror, the light bouncing back takes only a fraction of the tiniest moment to reach you. But when you look at a star, you're looking at something much older. The glow of a star 100 light-years away began its journey when people still relied on telescopes made from polished metal and hope. Look farther, and the timeline stretches thousands, millions, even billions of years. You are not seeing stars as they are. You are seeing stars as they were. This built-in time delay turns the universe into a museum, with each object displayed behind a window made of time. Astronomers make use of this cosmic museum by turning light into a measuring stick. If a galaxy is 10 million light-years away, we know its light took 10 million years to arrive. That number is more than a distance. It's a story, a travel log carried by ancient photons that began their trip long before Earth had complex life to receive them. But using this ruler is trickier than just counting the years, because the universe, in one of its more dramatic habits, refuses to stay still. Space is expanding, not like a balloon that someone inflated once and left on the kitchen counter, but like a balloon that never stops growing because the laws of physics insist on pumping more space into existence. This expansion means that light traveling through the cosmos is not moving along a fixed path. The path itself is stretching as the light moves. Imagine trying to walk across a floor that quietly grows longer with each step. No matter how fast you move, the finish line drifts farther away. The universe plays this game with every photon it sends us. This stretching of space has a very strange side effect. It stretches the light too. The wave gets pulled like taffy, its colors shifting toward the red end of the spectrum. Astronomers call this redshift, but you can think of it as the universe giving light a long, slow, cosmic tug. The farther away the galaxy, the more its light is stretched, and the redder it appears. So instead of just measuring how long the light took to reach us, astronomers must also measure how much it changed during its journey. Light becomes both ruler and message, a combination postcard and measuring tape that says, "Hello from the ancient universe. Also, the road has expanded since I left." This is where things get surprising. If you measure distance the way you measure it on Earth, kilometers, miles, light years, you might think a galaxy whose light has traveled for, say, 10 billion years must be 10 billion light years away. But that's the old-fashioned worldview. In an expanding universe, the situation is far more dramatic. The galaxy was much closer when the light left. But while the photon was traveling toward us, space itself stretched, dragging the galaxy even farther away. By the time the light reaches us, that galaxy is not 10 billion light years away. It might be 20 or 30 billion light years distant. The ruler stretched while we were using it. It's as if every measurement astronomers make comes with a tiny disclaimer. Warning, the universe has been rearranged since this light was emitted. Distances become conversations about what you mean by distance. Do you mean how far the light traveled? What the distance was back then? Or where the galaxy is now after billions of years of cosmic change? Each one gives a different answer, and somehow they're all correct in their own context. Using light as a ruler is both elegant and chaotic. Elegant because light always travels at the same vacuum speed and carries a record of its journey. Chaotic because the universe stretches the ruler as we measure with it. This stretching does not distort the information beyond use, but it does force astronomers to become mathematical contortionists. They must account for cosmic expansion, redshift, and the relative motion of galaxies themselves, all while dealing with light that started traveling long before humans knew what traveling was. One of the strangest consequences of this stretching ruler is that some objects are moving away from us so fast, because of expansion, that their light will never reach us. It is not that they outrun the light. They outrun the ability of light to close the ever-expanding gap. The universe can expand faster than light can travel, not because anything breaks the speed limit, but because space can grow without moving through anything. It's the difference between running across a field and having the field itself stretch beneath your feet faster than you can sprint. Eventually, some galaxies drift into a horizon beyond which their light is lost to us forever. They are still out there, but their stories will never arrive. Light is the greatest messenger the universe ever produced, but even it cannot keep pace with the growing fabric of existence, and yet that limitation becomes our tool. Every stretched wave, every shifted color, every delayed photon helps us map the universe's history. Light turns distance into time, redshift into motion, and cosmic stretching into a clue. By studying ancient light, astronomers read the autobiography of the universe, an autobiography still being written even as the ink dries billions of years later. Using light as a ruler may be messy, but it is the only ruler that reaches across the entire cosmos. And in its distortions, delays, and stretched out wavelengths, we find the universe telling us exactly how big it truly is and how endlessly it keeps growing. If you have ever wished you could send a message instantly across the universe, maybe to brag about discovering alien life, or to warn your future self not to microwave that questionable leftovers container, the universe has some disappointing news. No matter how clever you are, no matter how many sci-fi movies you quote at it, nature will not let information travel faster than light. Not because the universe lacks imagination, but because it is determined to keep causality in one piece. Causality, the rule that causes come before effects, is the cosmic equivalent of a no-tolerance policy. Break it, and the entire universe collapses into a giant, confusing timeline meme. But here is where it gets interesting. Light itself sometimes looks like it is cheating. In certain materials, its pulse can appear to leap ahead. In quantum tunneling, its wave seems to skip past obstacles faster than it should. In some exotic conditions, wave patterns stretch and reshape until they look like they are moving faster than the cosmic limit. If you only glanced at these effects, you might think physics is turning a blind eye and letting light pull off a few sneaky shortcuts. But the universe is far too strict for that. What is really happening is more subtle. A kind of cosmic stage magic where the appearance of speed does not match the actual transport of information. The key is to recognize the difference between the shape of a wave and the information it carries. A wave has parts: a leading edge, a crest, a peak, a tail, a signature. The information, the part that matters, is encoded in the earliest changes, the first hint that something new is happening. Scientists call this the front, and the front obeys the speed limit with a loyalty that would make a guard dog proud. No matter what trickery follows behind it, stretched peaks, shifted waveforms, bizarre distortions, the very first whisper of information never outruns light's vacuum pace. Imagine shouting across a canyon. The shape of your voice might echo, distort, or bounce. Some of those echoes might arrive sooner or later in weird ways depending on the canyon walls. But the first sound that reaches the listener is always bound by the physics of air. No echo will inform them before you do. Light behaves similarly. Its internal choreography can look strange, but the universe never allows the starting signal to travel faster than the ultimate limit. Quantum mechanics, mischievous as it is, also obeys this rule. Some phenomena seem to threaten the speed limit, like entanglement, where two particles separated by galaxies behave as if they share a secret handshake. Change one, and the other seems to update instantly, as though the universe sent a message faster than light. But here's the twist. Entanglement doesn't transmit information, it creates correlations, not communication. It is like two friends who always wear matching shirts without ever texting about it. Observers can't use entanglement to send messages because there is no way to control the outcome on either side. Nature built the system so tightly that even its spookiest effects remain gossip-proof. Even more deceptive is quantum tunneling. In tunneling experiments, the peak of a light pulse can appear on the far side of a barrier sooner than expected. It looks as though the photon just shrugged at physics and walked through the wall faster than possible. But the pulse that emerges is not carrying fresh information. The earliest possible change, again the front, is still limited by light speed. The pulse looks early because the barrier filters the wave, shaving off some parts and letting others pass. The pulse is changed, not transported faster. It is the cosmic equivalent of squeezing a water balloon so the bulge pops forward. It moves, but the water didn't teleport. Nature enforces this rule because faster than light communication would shred causality like confetti. Imagine sending a message into the past. You could warn yourself of mistakes, undo events, or create contradictions that spiral into logical chaos. Physics is not built to handle timelines that loop like tangled spaghetti. So instead of letting us run wild, the universe locks the speed limit into the very architecture of space-time. Information must follow paths that maintain cause and effect order. No shortcuts, no loopholes, no maybe if we try this wild setup at 3 a.m. exceptions. This is why physicists describe light's speed as the speed of causality. It is not about photons traveling quickly. It is about how the universe defines the maximum rate at which influence can spread. Every signal, every push, every gravitational ripple, every quantum nudge must respect this boundary. Even gravitational waves, the ripples from colliding black holes, travel at the same speed. They are nature's loudest events, and even they cannot gossip faster. This cosmic policing might feel restrictive, but there is something elegant about it. The speed limit knits the universe together into a coherent whole. It ensures that events unfold in a way that makes sense, that histories cannot undo themselves, that the universe's timeline stays intact. If information could outrun light, the entire fabric of space-time would unravel into paradoxes, so confusing even physics would need a long nap. And yet, within this strict limit, the universe still offers an incredible amount of creativity. Waves can stretch, shapes can shift, correlations can span galaxies, and photons can dance along the edges of possibility, all without breaking the fundamental rule. Nature allows illusions, not violations. If light looks like it's cheating, it is only because the universe enjoys a dramatic flourish now and then. So while we may never send cosmic gossip faster than light, the restrictions are not flaws. They are the reason the universe's story makes sense. And within those boundaries, light still carries every message we could ever hope to send across distances vast beyond comprehension at the fastest pace reality allows. If you ever find yourself staring into the core of a nuclear reactor, hopefully from behind several feet of reinforced shielding, because curiosity is admirable but survival is practical, you'll notice something eerie. The water surrounding the core glows a vivid, ghostly blue, like someone submerged an entire science fiction movie under the surface. It's not a special effect. It's not luminescent paint. It's not some reactor operator sneaking in fancy aquarium lights. That glow is Cherenkov radiation, one of the universe's most dramatic announcements that something incredibly fast just happened. Specifically, a charged particle outran light. Now, before you report this to the cosmic authorities, let's clear something up. These particles are not breaking the universal speed limit. They have not achieved the impossible. They simply found a loophole, but a legal one, because the speed limit they exceeded wasn't the speed of light, only the speed of light in that material. Light slows down in water, glass, and other substances because it's constantly bumping into atoms like a tourist weaving through a packed market. But particles like electrons aren't bound by the same stop and start delays. If you accelerate an electron fast enough, say during a nuclear reaction, it can zoom through the material faster than light manages to, creating the photonic equivalent of a sonic boom. This is the heart of Cherenkov radiation. When a charged particle blasts through a medium faster than light can move in that medium, it creates a shock wave of electromagnetic energy, and that shock wave manifests as a distinctive bright blue glow. It is, in essence, light's version of "you just got past." The universe cannot resist making a spectacle out of the moment. To understand why this happens, think about what occurs when something breaks the sound barrier. A jet traveling at subsonic speeds sends pressure waves ahead of itself, create a disturbance. Wait for it to propagate. But once the jet pushes past the speed of those waves, it plows through them faster than they can move, causing the waves to pile up into a cone-shaped shock. That shock is the source of a sonic boom. Now replace pressure waves with electromagnetic fields and air with a transparent medium, and you have the EM equivalent, a photonic boom that emits blue light instead of a thunderous crack. But here's where Cherenkov radiation gets even more fascinating. The glow isn't just random light scattered in all directions. It emerges at a specific angle, forming a cone around the particle's path. If you could freeze time and photograph a single instance, you'd see something that looks like a glowing arrowhead stretching out behind the speeding particle. In a way, the blue glow is not just a sign of speed, it's a map of the particle's motion, a luminous fingerprint of its path through the medium. The reason the glow appears blue rather than red or green has to do with how different wavelengths of light are produced by the shock wave. Higher energy, shorter wavelengths, the kind associated with blue, dominate the radiation. Nature could have made Cherenkov radiation a rainbow, but it chose a color that looks like distilled science. Blue is the universe's equivalent of highlighting a sentence in neon marker. In nuclear reactors, Cherenkov radiation is almost a language. It tells engineers that charged particles are flying around at breakneck speeds as part of the nuclear chain reaction. The glow is a signature of energetic electrons released during radioactive decays. In fact, the clarity of the glow can help operators visually gauge certain conditions inside a reactor. It's not exactly a user interface, but it's pretty close for something that predates human technology by billions of years. Cherenkov radiation also shows up in unexpected places. Deep underground laboratories use huge tanks of ultra-pure water to detect neutrinos, ghost-like particles that barely interact with anything. When a rare neutrino collision occurs, it produces a charged particle moving fast enough to create a faint Cherenkov glow. Scientists surround the water with light sensors, waiting for that blink of blue to reveal that a neutrino has finally tapped on the universe's door. It's cosmic hide and seek, but with radiation instead of children yelling, "Found you!" The same principle applies in astrophysics. High-energy particles arriving from space can streak through Earth's atmosphere faster than light, can move through air. The result is a brief, but detectable Cherenkov flash. When multiple flashes appear in a pattern, scientists can trace them back to their origin, perhaps a distant supernova, or a black hole hurling particles across the cosmos at absurd energies. Cherenkov detectors become windows, not just into nuclear reactors, but into the violent, restless engines of the universe itself. What makes Cherenkov radiation so mind-bending is that it blurs the line between faster-than-light illusions and the strict order the universe enforces. These particles aren't breaking the ultimate rule, they're breaking a local speed limit. It's like going faster than the posted speed on a back road while still obeying the highway's maximum. The cosmic police won't pull you over because the real limit, the one built into spacetime itself, remains intact. Light inside a material is slowed by incessant interactions, but particles can shoot through without the same hindrance. So when an electron outruns light in water, it's not defying the universe. It's simply taking a shortcut through a crowded room while light stops to greet everyone it passes. Cherenkov radiation is a reminder that even the most rigid-seeming cosmic laws have nuance. The universe enforces its rules with precision, but it also leaves room for spectacular phenomena that flash electric blue in the depths of reactors, trace the path of ancient neutrinos, and help us detect particles from realms light years away. It's physics at its most dramatic. Particles so fast they make light glow in protest. When people imagine the future, they often picture sleek spacecraft whispering across the galaxy at impossible speeds, conversations beaming instantly between distant star systems, and humans hopping around the cosmos like someone checking off destinations on a very ambitious vacation list. But the universe, being a pragmatic architect, reminds us that even in the most advanced future we can dream up, information and matter cannot outrun light. That limit is both the universe's firmest rule and its greatest design challenge. Instead of breaking it, future technologies will have to work with it, bend around it, or cleverly sidestep it without crossing the forbidden line. And surprisingly, some of those possibilities are not just sci-fi fantasies. They are ideas rooted in physics that, while currently impractical, shimmer with that irresistible blend of ambition and plausibility. Start with something deceptively simple: communication delay. Even with our current technology, this delay shapes how we interact with space. A radio message to the moon takes a little over a second. Mars is far worse. Depending on the planet's positions, a message can take anywhere from several minutes to nearly half an hour. If astronauts on Mars wanted to play an online game with people on Earth, every round would involve waiting longer than it takes to microwave dinner. And that's just Mars, the cosmic next-door neighbor. Send a message to a spacecraft heading to the outer edges of the solar system, and you are waiting hours. Talk to another star. Forget minutes, forget hours. Those delays stretch into years. If you sent a message to a planet 50 light years away, the earliest possible reply would reach your great-great-great-grandchildren's inbox. These communication lags shape what future space exploration will look like. Colonies on other planets will need to function independently, Not because of courage alone, but because calling home for help would feel like writing a letter by candlelight. Engineers will develop smarter autonomous systems, spacecraft that diagnose themselves, and habitats that make their own decisions. In the future, the distance between planets won't just be miles. It'll be moments of time that ripple between societies, shaping their rhythms, their politics, and their cultures. But even with those delays, humanity will push for faster ways to share information across the cosmos. One area ripe for development is quantum communication, often portrayed as instant, but in reality constrained by the same cosmic rulebook as everything else. Entanglement, quantum particles mirroring each other's states across distance, creates correlations, not messages. You cannot whisper instructions into one particle and have the other shout them across the universe. But what entanglement can provide is security. A quantum network could detect eavesdropping instantly, because any disturbance changes the delicate quantum state. Future interplanetary communication might rely on this, slower than science fiction dreams, but far safer. You might wait 15 minutes for a message from Mars, but at least you know no one tampered with it along the way. That's the pragmatic side. Then there's humanity's more exuberant ambition. If we cannot move faster than light, maybe we can move space itself. Enter the idea of warp drives, not engines that accelerate you beyond the cosmic limit, but engines that reshape space-time so the limit applies differently inside your bubble of reality. It sounds like the kind of scheme a mischievous physicist would propose after too little sleep and too much coffee, but the mathematics is surprisingly legitimate. The most famous design is often associated with Miguel Alcubierre, who proposed a theoretical framework where space behind a spacecraft expands, while space in front contracts. The ship itself sits inside a calm region of space-time, like a boat floating in a bubble while the river rushes around it. You are not speeding through space. Space is doing all the moving. Since space-time can expand faster than light without breaking any rules, as we see in the expanding universe, this bubble could carry a ship from one star to another faster than light could have gotten there on its own, all while obeying the cosmic speed limit locally. It is a loophole of such cosmic finesse that even nature would have to applaud it. The problem: it requires energy densities that make stars look underfunded, along with exotic forms of matter we have never observed. It is the engineering equivalent of deciding to build a skyscraper out of unicorn feathers. But theoretical difficulties have rarely stopped humans from dreaming. Scientists continue probing the boundaries of how space-time can curve, twist, or fold. Maybe the future holds a scaled-down version, something that nudges space-time rather than bulldozing it. Another concept involves wormholes, bridges through space-time connecting distant regions. If a warp drive bends space smoothly, a wormhole folds it dramatically. Instead of taking the long road, you cut through the fabric like threading a needle through dimensions. The math allows such structures, but just like warp drives, the practical requirements resemble asking the universe to hand over ingredients it does not seem to stock on any shelf. Still, the possibility tempts physicists because wormholes solve the same problem warp drives tackle: The universe refuses to let you exceed light speed, but it never said you had to take the long way. And meanwhile, back in the realm of technologies we can currently imagine building, photon-based propulsion continues to evolve. Solar sails driven by sunlight or powerful lasers could accelerate spacecraft without carrying massive fuel supplies, slowly nudging them to high fractions of light speed. It would not be instant travel, but compared to chemical rockets, it is like trading a rowboat for a turbocharged ship. Missions to nearby stars would still take decades, but decades are a vast improvement over millennia. The future of light-speed technologies is not about breaking laws. It is about learning how to dance with them. Light remains the universe's fastest messenger, but humanity's dreams stretch beyond mere messages. Whether through quantum-secure communication, photon-driven spacecraft, or the distant possibility of bending space-time, the future will hinge on our ability to understand the cosmic speed limit, not as a barrier, but as a boundary rich with creative shortcuts. In the end, the universe keeps its rules tight, but it leaves just enough room for ingenuity to flourish. And inside that narrow, extraordinary space, our future technologies will rise. From the very beginning of our relationship with light, we treated its speed like a universal punchline. Here is the fastest thing in existence, the unbeatable champion, the cosmic cheetah. Teachers told us that light travels at a fixed pace. Astronomers nodded sagely, and science textbooks carved the number into our memories like cosmic graffiti. But after wandering through the universe's deeper halls, vacuum highways, atomic traffic jams, gravity-warped detours, plasma illusions, and quantum sleights of hand, it becomes clear that the speed of light is not the neat, polished fact we once believed it to be. It is stranger, wilder, more dramatic, and far more alive than any number printed on a chart. By now, you've seen that light behaves like a cosmic shapeshifter. In empty space, it races freely as though nothing could ever slow it down. Introduce it to matter, and suddenly it trips, stumbles, pauses, and negotiates its way forward like someone politely squeezing through a crowded subway. In exotic materials, light can crawl at speeds that make snails look reckless. In carefully tuned experiments, scientists can hold it still, freezing its identity like a paused video frame. Yet at the opposite extreme, there are environments where light's patterns seem to leap ahead as though they just remembered an appointment. Plasma storms in the early universe and exotic metamaterials here on Earth can make light look as if it has jumped the line, outrunning its own shadow. But beneath every bizarre scenario lies the same truth. The universe closes every loophole with elegant precision. Nothing that carries information outruns the true cosmic limit. Light's illusions are clever, but they never break the rule book. Then there is space-time, the invisible architecture that light uses as its stage. Far from gliding over a flat, motionless surface, light travels across a landscape shaped by the weight of stars and the gravity of galaxies. Its journey becomes warped, stretched, and curved, as if space-time were a mischievous tour guide insisting on the scenic route. And even when the universe expands beneath its path, stretching the road like cosmic taffy. Light does not slow down. Instead, the wavelengths stretch with the expansion, turning color into a record of distance, age, and the universe's constant growth. So the speed of light is many things: a measurement, a boundary, a messenger, a performer, a tracer, a time machine, and a rule enforced with cosmic resolve. But perhaps most surprisingly, it is also a choice. Not in the sense that light gets to decide how fast it will move. It is not that rebellious, but because humanity chose to define its speed precisely. We set the number in stone, and in return, light let us reconstruct the meter, calibrate the clocks of civilization, guide spacecraft through the void, and synchronize the heartbeat of global communication. The number is ours, the behavior is the universe's. What remains after exploring all these layers is the realization that speed, when applied to light, is not really about motion at all. It is about structure. It is about how electric and magnetic fields pulse together, how space-time curves beneath mass, how matter interferes, how information flows. Light moves at the speed it does because the universe is built the way it is. To change light's speed in a vacuum, you'd have to rewrite the architecture of space-time, the cosmic equivalent of remodeling reality's foundation while standing on it. And yet, despite all of this complexity, we encounter light every day as if it were the simplest thing in the world. We flip switches, open curtains, watch sunsets, take photos, and bask in the glow of screens, without thinking about the elegant machinery behind every photon. Every beam of light, from the flicker of a candle to the glare of a star, carries with it the full weight of the universe's rulebook, obeying constraints so deep and fundamental that our entire reality hangs on them staying consistent. But light is not just a rule follower, it is also a storyteller. Every time light reaches your eyes, it brings history. Distant galaxies show us their childhoods. Ancient starlight offers glimpses into epochs long gone. Even the glow from your phone's screen is a tiny performance of electromagnetic choreography, repeating billions of times per second. Light takes what is happening somewhere and makes it appear somewhere else. It is a courier distributing the universe's news, with delays, detours, distortions, and all the drama you'd expect from a cosmic messenger working overtime. If this journey has shown anything, it is that the speed of light is less like a number and more like a character, a main character in the story of the cosmos. Its speed sets the pace for the universe's unfolding narrative. Its limitations protect causality. Its constancy defines the shape of space and the rhythm of time. Its interactions with matter create the world as we see it, and its strange behaviors in extreme environments remind us again and again that nature has layers far deeper than our initial assumptions. The next time you hear someone recite the speed of light as a simple fact, you can smile knowing the truth. That number is only the surface. Beneath it lies a web of complexity that stretches from the hearts of atoms to the edges of the universe. Light is fast, yes, but its story is even faster. And now that you've traveled through that story, you're carrying a little bit of cosmic illumination yourself, not just about how quickly light moves, but about how profoundly it shapes everything we know. If the universe were a movie, light wouldn't just be the special effects. It would be the director, the narrator, and the soundtrack rolled into one. And the speed of light? That's not just how fast something can travel. That's the tempo of reality.